Good morning, friends. It gives me immense pleasure to be here again for my course Engineering Thermodynamics. I am Dr. Dwivedi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I am in the process of delivering Engineering Thermodynamics. I have completed all the 5 modules of this course, and this is my last lecture from the topic from this course. And after that, I will be discussing about the definition and the terminology of this 5 lectures, and the 5 lectures after this will be the questions and answers. Lot of questions and answer will be discussed. So after this class, I will have 10 more lectures related to the different modules. For each module, I will have one class for the definition and the terminology, and for one class, I will have the question bank and their answers. So after this class, it will not be new thing. So many things will be also repeated, and some questions I will be taking, some new innovative ideas I will be delivering in this next 10 lectures. But today I am going to take about heat transfer numerical problems, and in this heat transfer numerical problems, I am going to take 4 problems. Those 4 problems are related to the conduction, convection, and different types of questions. They are very much interesting for the this course. So we will see here that numerical problem 1, it is for the heat conduction. Numerical problem 2, it is also heat conduction. So here I am going to take the four problems. So the first problem I am here discussing, I am going to read this. A 7.5 centimeter thick side wall of an oven is primarily made of insulation with conductivity of 0.04 watt per meter Kelvin. Conditions of the inside of the wall having fixed temperature of 420 Kelvin. The electric coil within the oven dissipate 36.5 watts of electric energy to make up for the heat lost during the wall. Calculate the wall surface area perpendicular to heat flow so that temperature on the oven side of the wall does not exceed 310 Kelvin. So a very interesting and very practical problem, and most of the problems which I have taken is from the Senegal, and Senegal has given the very good practical problems. So here the thickness of this side wall is 7.5 centimeter. Primarily made of the insulation, the conductivity, this is the K, and here it is the X. Conditions of the inside of the wall having the fixed temperature of 420 Kelvin. So this temperature of the wall is fixed as a 420 Kelvin. The electric coil within the oven dissipates 36.5 watts of electrical energy to make up for this heat lost through the wall. Calculate the wall surface area. So we have to find out wall surface area. A we have to AS. It is called AS. AS is how much to heat flow so that temperature on the oven side of the wall does not exceed 310 Kelvin. So these are the parameters which are given in this problem. So we will see here that given is K is equal to 0. It is a conductivity. K is equal to 0.04 watt per meter Kelvin. Temperature T1 is given as a 420 Kelvin. T2 temperature of this is given 310 Kelvin. The thickness delta is given 7.5 centimeter. We can make it 7.5 into 10 to the power minus 2 meter. And the heat transferred is 36.5 watts. Find the area. So we have to find out the area. So we know the heat transfer Q is given by the conduction. It is by the conduction. Q is equal to Ka T1 minus T2 by delta. So Q is given 36.5 watt. K is given here 0.04. A we have to find out. 420 is the highest temperature and 310 is the lowest temperature, and divided by delta is given here 0.75. So this will be 0.75 meter. So if you take A in this side, so this will be 36.5 into 0.75 divided by 0.04 into 420 minus 310, it will be 110. So if you calculate this, you will get 6.21 meter square. This is the area of that perpendicular of this. This much area is required for the conduction of this heat. So what is the importance of this? You know that if you take our engine, in engine you have so many baffles like this, both sides. Okay, I think you might have seen like this. Fins are there. These fins, because this much area, 6.21 meter square, it is very big area. Means if you take here 3 meter by 2 meter, 3 meter by 2 meter, this much area you can't get. So we have to make by different small portion, and we have to make 6.21 meter area by small thin fins. We have to add it, and this area we can increase area by using the fins. So we have done with the first numerical. Now I think we will go for the second one. So this second numerical is a plain wall of 10 centimeter thickness. So here the delta is 10 centimeter. Area is AS is given 3 meter square surface. Area is made of the material whose conductivity K is 8.5 watt per meter centigrade. The temperature of the wall surface are at 100 degree centigrade and 30 degree centigrade. So T1 and the T2, K, A, and so what we have to find out? So here we have to find out the rate of heat transfer. Okay, so here find rate of heat transfer, Q. This we have to find out. Mostly all the values are here given. So here the thickness is 10 centimeter. It is equal to 0.1 meter. Area is equal to 3 meter square. Conductivity is 8.5 watt per meter centigrade. T1 is equal to 100 and T2 is equal to 20 degree centigrade. I think here it is 30. So 30 degree centigrade. So the temperature gradient is given by dt by dx. dt by dx is equal to T2 minus T1 by delta. T2 is equal to 30 minus 100 by 0.1. So you will get minus 700 degree centigrade. So this is the temperature gradient. Heat flow rate Q is given by the Fourier's equation. So this Q is equal to minus Ka T2 minus T1 by delta x. So minus K is equal to 8.5 here, A is equal to 3, A is equal to 3 meter square, and here is a minus 700. So if you multiply it, Q you will get 17850 watt. Okay, so we can make it as a 17.85 kilowatt, and this much heat is transferred. So heat is transferred at 7.85 kilowatt. So this is the solution for this problem. Now I will go for the next problem, and we will see here that a furnace wall comprises 3 layers, that is 13.5 centimeter thick inside layer of fire brick, 7.5 centimeter thick middle layer of insulating material, and 11.5 centimeter thick outside layer of composite wall to be maintained at 40 degrees centigrade circulating air. Assuming close bonded layer of their interfaces, find A, rate of heat loss from the furnace, Q, wall interference temperature, T. Wall measures 5 meter into 2 meter area. So area is equal to 10 meter square. The conductivity of the brick, fire brick, is K1 is equal to 1.2 watt per meter degree centigrade. Insulating brick K2 is equal to 0.14 watt per meter degree centigrade. Red brick K3 is equal to 0.85 watt per meter degree centigrade. These are the parameters which are given. Now, so here we have the 3 layers of material, and these layers we have to find out the rate of heat loss and the temperatures at different locations. So now we will see that solution. First we have to draw the diagram. So here you can see here, this is the fire brick here, this is the insulation brick, and this is the red brick. K1, the length of this thing is 13.5 centimeter. Length of the insulating brick is 7.5 centimeter. Red brick is 11.5. Area of cross section is 2 meter by 5 meter. Here it is 870 degrees centigrade, and here it is leaving 40 degrees centigrade. The surface of this thing is T1, surface of this thing is T2, surface of this thing is T3, surface of this thing is T4, which is the 40 degrees centigrade. So we know the initial and the last temperature, we know K1, K2, K3, we know the area, we know this distances. So we have to calculate the heat transfer by this equation. So we will see here that total heat loss Q equivalent is equal to delta T divided by total resistance. This delta T is equal to here T1 minus T4. T1 is given, T4 is given. So T1 minus T4 divided by total resistance. So how much is the total resistance? It is divided by delta 1 by K1A plus delta 2 by K2A plus delta 3 by K3A. So we have to find out the RK1. So this we can say as a RK1, this is as a RK2, and this is as a RK3. So this RK1 is equal to delta 1 by K1A. Delta 1 is equal to 13.5 into 10 to the power minus 2 divided by K1 is 1.2 and area is 5 into 2. So the value of this thing, you will get 0.01125 degree per watt. Then we will see the resistance of this insulator is delta 2 divided by K2A, 7.5 into 10 to the power minus 2 divided by 0.14 into 5 into 2 is equal to 0.05357 degree per watt. And same way for the resistance for the third wall is delta 3 by K3A is equal to, this is here 11.5, 11.5 into 10 to the power minus 2 divided by K3. K3 is 0.85. Area is equal to 5 into 2. You will get 0.1252 degree per watt. So we got R1, R2, R3. Total resistance or R equivalent is equal to RK1 plus RK2 plus RK3. This. We will add it. We will get here 0.78349 degree per watt. So we got this resistance and we know the T1 and we know the T2. So now we can find out the Q. So we will see here, to find the heat loss Q is equal to T1 minus T4 by RQ, R equivalent. T1 is equal to 870 degrees centigrade. T4 is equal to 40. R equivalent is equal to 0.78349. So we can get Q is equal to 1059.57 watt or 1.059 kilowatt. So we got the one answer, but we have to find out the temperature T2 and the T3. So how to find out? This heat transfer rate will be same. Okay, however, here RK1 we know the T1, we can find out the T2. So this heat transfer rate is equal to T1 minus T2 by RK1. We know that T1, we don't know this, we know this one. So we know this Q is equal to 1059.57. So by this calculation, we can get the temperature is equal to 750.82 degrees centigrade. And so temperature of the first junction, that is called the T2, is equal to 750.82 degrees centigrade. Now we have to find out the temperature of T3 between the insulator and the last junction, that is called the T3. Same equation we have to use. Q is equal to T1 minus T2 minus T3 by RK1. T2 we have find out just now. This is the T2 minus T3 divided by 0.05357. You will get is equal to 1059.57. So you will get this temperature, junction temperature, second junction temperature T3 is equal to 183.33 degrees centigrade. And so temperature of the third junction is T3 is equal to 183.33 degrees centigrade. So this also answer we got. So these three answers were asked, that is how much is the heat rate transfer, how much is the temperature between the first junction to the second junction, and from second junction to the third junction. So we find out the Q, T2 and the T3. So in this way, you can find out that at what level, how much temperature you are having. From that, you can do your calculation, you can design the material. What type of material in this insulation is required? What type of the material after the insulation is required? So as an engineer, as a designer, we should understand the basic concept of the heat transfer. Then only we can design the system. Now, this is the last numerical of this class, and it is a numerical number 4. A 80 centimeter thick wall of reactor is made of an inner layer of fire brick. K1 is equal to 0.85 watt per meter Kelvin, covered with a layer of insulation. K2 is equal to 0.15 watt per meter Kelvin. The reactor operates at a temperature of 1600 Kelvin, whilst the ambient temperature is 295 Kelvin. So what we have to calculate? Calculate the thickness of the fire brick and the insulation. We have to find out how much it should be the thickness delta for the fire brick and for the insulation, which gives minimum heat loss. Also work output heat loss, presuming that the insulating materials has a maximum temperature of 1475 Kelvin. If calculated heat loss is unacceptable, would the addition of another layer of insulation be a satisfactory? So very nice question, and we have to go step by step for this solution. So we have to draw the diagram. So here we have one is brick, another is the insulation, and total thickness is 30 centimeter. So we have to assume that from T1 to T2 the thickness is X. So remaining will be 30 minus X. K1 of this material is given 0.85 watt per meter Kelvin, and this K2 is given 0.15 watt per meter Kelvin. The temperature at T1 is 1600 Kelvin, T3 is a 295 Kelvin, and in between it is a T2 is given 1475 Kelvin. These parameters are given, so we have to find out this distance and this distance we have to find out. So here the total length of the system is 30 centimeter. It is given. Let the layer of the first slab be the X. So the next slab will be 30 minus X. K1 is equal to 0.8 watt per meter Kelvin. K2 is equal to 0.15 watt per meter Kelvin. T1 is equal to 1600 Kelvin. T2 is equal to 1475 Kelvin. T3 is equal to 295 Kelvin. Let's find the X first. We know the rate of heat transfer from T1 to T2 will be equal to the T2 and the T3. So rate of heat transfer from each slab will be the same. So this Q is equal to, so T1 minus T3 divided by X K1A plus 30 minus X K2A. This is equal to T1 minus T3 X by 0.85. Okay. So now if you see here, T1 minus T3, T1 minus T2. So here T1 minus T3 is equal to X by 0.85 plus 30 minus X 0.15 is equal to T1 minus T2 X by 0.85. Now putting the given values in this equation, we know T1 is equal to 1600, T3 is equal to 295, T2 is equal to 1475. And so 1600 minus 295 divided by X 0.8 X by 0.85 plus 30 minus X divided by 0.15 is equal to 1600 minus 1475 X by 0.85. Now if we simplify 1600 minus 295, you will get 1305 divided by X by 0.85 plus, here if you divide this thing you will get 2 minus X by 0.15. Here you will get 125 X divided by 0.85. So if you multiply this thing here and this thing here, you will get 1305 into X is equal to 212.5 minus 583.31 X. So from here X you will get 0.1125 meter or 11.25 centimeter. So we know that we have assumed that total here, this is the X, T1, T2 and the T3. So this is 30 minus X, as total this thing is 30 centimeter. So you got this X. So 30 minus X, you will get, this is 11.25 centimeter and this is 18.75 centimeter. So this is the answer for this. The thickness of this system will be 18.75 centimeter for T2 to T3, and from T1 to T2 the thickness will be 11.25 centimeter. So now we can find out the flux. Flux is equal to T1 minus T2 by X by K1. So here 1600 minus 1475 divided by 0.1125 by 0.85, you will get 944.45 watt per meter square. So heat loss per unit area is flux. So this heat loss per unit area, you will get 944.45. So this is the answer for the problem. So I have taken the references from Eunice Senegal, Michael A. Bors, Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition. Any questions, you are welcome to ask. My email is ydwedi@gmail.com. Please do like and subscribe my channel. This is my end of the course. However, I will be having next 10 classes, 5 classes for definition and the terminology of engineering thermodynamics. I will cover all the modules 1, module 2, module 3, module 4 and module 5. And next 5 lecture will be the question answering with some important question answer with numericals. I will be again solving for the 10 lectures. Thank you very much for the joining, and I really appreciate your efforts and your patience to listen me, and I really request from you to give me the feedback so that I can improve myself. Whenever I do some mistake, you are the person to guide me. Thank you very much for the joining. Till then, goodbye and see you.
Like, share and subscribe. Hit the bell icon for more updates.